Hey guys. All right, welcome to our first digital note-taking experience. So we are going to take some notes today, moving on in your packet. So you need your packet, and you're also probably going to want some sort of calculator, whether it's your graphing calculator or just the calculator on your phone, but something just to do some simple addition and subtraction on would probably be helpful today. So I am on page 9, I believe. Let me double check that. Yes, page 9 in your packet here, section 10.3. So after your quiz on Friday, you were supposed to write down some definitions for some terms that are going to come up in this section. A lot of you have asked me, do I need to submit a picture of that? So if you already have that written down, then you probably don't need to copy down what I have on the screen right now. But if you didn't do that, then you might want to pause the video for a second and fill in these definitions. I'm going to talk about all of them in just a sec, but if that's information that's helpful to you to actually have written down, especially if you didn't already do that, then go ahead and just pause the video for a sec and get those definitions copied down. If you did already do that on Friday, it's just for you to have. It should make this a little bit easier today, taking these notes. So there's nothing from last week that you need to worry about submitting to me. Everything moving forward is everything that's going to be submitted will start with this week. So looking at this picture here. So I'm going to kind of use the picture to talk about the definitions and what these terms mean. So some of these might be words that you're familiar with that you've seen before. So first of all, a chord. In a circle, a chord is simply a segment that goes from one side of the circle to the other. And it doesn't necessarily have to pass through the center of the circle. So if you look at this picture here, for example, IH, that segment right there, that's a chord. So it's not passing through the center, it's just going from one side of the circle to the other side of the circle. So one of the chords in this picture would be segment IH. That little line on the top just means segment. The other chord in this picture is actually going through the center. So not only is it a chord, but it's also a diameter. So this segment right here, FG, is going from one edge of the circle to the other. So that makes it a chord. So we would add that here. FG is a chord, and it's also a diameter. So a diameter is specifically a chord that's passing through the center. So it's a special type of chord. A tangent. So a tangent is a line, first of all. So it continues on forever. And it's a line that hits the circle exactly one time. So we say technically that it's crossing the circle, but it's not actually going through the circle. It's just kind of like brushing up against the side of the circle. So in this picture here, that's happening with this line on the edge, JK. So line JK would be the tangent line in this picture. And then the point, the one point where that line and the circle touch, that point right there is called the point of tangency. So I've now covered it up with all of my green, but that would be this point right here, which was point I. A secant. So a secant is also a line, and it's a line that crosses the circle twice. So the tangent crosses the circle once or touches the circle once, and the secant or a secant is a line that basically just cuts through the circle anywhere. So that would be this line right here. LM is our secant in this picture. We'll talk about the inscribed angle and the outside angle in just a second. A radius, we've already talked about that. That's the segment that goes from the center of the circle to the edge. So in this picture, there's two of them. Both of them are basically just the two halves of that diameter. So we have a radius from E to G, and then also from E to F. So EG is a radius, and EF is also a radius in this picture. So that basically goes through those vocab words up there. So talking now about inscribed angles and outside angles. That's really what this section is mostly about. So hopefully you already watched those two kind of intro videos so that you have a little bit of background. So if you recall from last week we talked about central angles. So a central angle has its vertex at the center of the circle. So in this picture here, angle AOC, that's our central angle because its vertex is the center of the circle. The inscribed angle, so this is the new one, the inscribed angle is the angle whose vertex is on the circle. So it's kind of like we're taking that center vertex and pulling it out to the edge of the circle. So in this picture, angle ABC, that's our inscribed angle. So the central angle is created by two radii. That's the plural for radius. The central angle is created by the two radii. So the central angle is created by AO and CO here. An inscribed angle is created by two chords. So it's created by those two segments that are going from the edge of the circle to the edge of the circle. So the chords in this picture creating that inscribed angle are AB and CB. So a word or a term that we haven't really talked about a whole lot yet, but that's going to be really important in this section is what's written here and being called an intercepted arc. So the intercepted arc for both of these angles, for the central angle and the inscribed angle, is the arc intercepted. Think of it as like it's the arc that those angles intercept. It's the arc that those angles kind of cut off on the circle. So for both of these angles, they have that same intercepted arc. They both have the arc AC as their intercepted arc. If we extended the sides of either of those angles, that's kind of where they would cut through the circle and they would leave that piece of the circle in the middle. So that's what the intercepted arc is. So we'll kind of fill this in again on the next page of your packet. But one of the things that you saw hopefully in the video, and one of the most important parts of this whole idea of an intercepted arc and central angle and inscribed angle. So the central angle equals the arc. They are exactly the same measurement. If the central angle is 50 degrees, that arc is 50 degrees and vice versa. The inscribed angle, again, if you think of it as kind of pulling that vertex back to the edge of the circle, so you're shrinking that angle when you do that. So the inscribed angle is half of the arc. So if the arc is 50 degrees, the inscribed angle is 25. If the inscribed angle is 25, the arc is 50. So that's a really important relationship. So central angles and arcs have the same measurement. Inscribed angles are half of that arc measurement. So we're going to use that relationship now on the next page to find some missing measurements. So the theorem for inscribed angles, it's what we just said, that the measure of the inscribed angle is half of the measure of its intercepted arc, which also means that it's half of the measure of that central angle, which is also going to be pretty helpful to us when we're finding missing measurements. So I know that this seems like a lot of things to remember right now. Just keep in mind that given the fact that we're doing this the way that we are, we're going to keep things pretty basic. So you're going to see in a second, we're going to skip a lot of the problems that are in your packet today because I think it's way more important that you just understand the concepts and can apply them in a basic scenario. And we're not going to do a lot of problems that are super involved in this section. So just do your best to not get overwhelmed right now, because I think that you'll see that once you start to practice these, they're pretty easy. All All right, so we are just applying this relationship now in all of these angles. So in number one, we are looking for this inscribed arc right here. Inscribed angle. That's an inscribed angle, and we know that because its vertex is on the circle. So the inscribed angle is half of the arc think of the intercepted arc kind of as the arc that's inside of it. So it's half of that arc. So if the arc is 170, half of that is 85. So that angle would have a measurement of 85 degrees. So number two looks a little bit more complicated because it has the triangle there, but keep in mind that we still just have a triangle is just that, triangle, it's three angles. So when you have that triangle, it's just creating three inscribed angles. So we're looking again for the measurement of an inscribed angle, this angle here. Sometimes it helps if you extend those sides out like I'm doing. So the measurement of this angle is going to be half of its arc. If its arc is 118, then 118 divided by 2 is 59 degrees. So to find the measurement of the inscribed angle, not the central angle right now, but inscribed angle, we just divide that arc by 2. All right, number 3. So again, I know this picture looks a little overwhelming, but try to break down what you're looking for. So this time we're looking for the measurement of an arc. So the angle that's creating that arc is this angle right here. That's the inscribed angle creating the arc that we're looking for. So now we're going to apply that property in reverse. If we know the arc, we divide by 2 to get the angle. If we know the angle, then we're going to multiply it by 2 to get our arc. So this arc would be 96 degrees. Okay. All right, last picture here, number 4. So this time we're looking for an angle again. If we extend our sides, here's our intercepted arc. So we know that it's going to be half of that. Unfortunately, this time that measurement isn't there. It's not labeled for us. So we have to use the other information that we have to figure that out. So if you look at this picture, we have a diameter. So we have 180 degrees on this half of the circle. If we've accounted for 100 of them, there are 80 degrees left in the arc that we're looking at. And then when we divide that 80 by 2, we figure out that our angle is 40 degrees. Okay, so all of the rules and properties that we learned last week, they still apply. So you can use all of those relationships to find missing arcs and angle measurements that might then help you to find information that you need. All right, so the last kind of important thing about inscribed angles, I'm actually going to erase real quick some of what I did in number 4 so that you can see this. So I know that we found just a second ago that question mark angle, but I want you to look now remember that we said a triangle is actually 3 inscribed angles. So look at this angle right here. Okay, so when the angle that's created, when its endpoints create a diameter, that's what's happening here. We have a diameter. Then this is a semicircle. So its intercepted arc is 180 degrees. That means then that this would be half of that, which is 90 degrees. So this is true for every diameter. When the endpoints form a diameter, when you have an angle, when you have an inscribed angle and the endpoints to that angle form a diameter, that's always going to create a right angle or a 90-degree angle. So that's just kind of a special property that happens with inscribed angles. All right, so the last little bit of these notes, the outside angles. So basically what we've been doing is, if you think about a circle, we started with the central angles. So we started with angles whose vertex was at the center of the circle. Then we moved that to the edge of the circle, and we talked about inscribed angles. So the last piece of this puzzle is that we move that vertex outside of the circle. So we're kind of gradually pulling the angle back out of the circle. So an outside angle is when your angle has a vertex that's outside of the circle. So the measurement for these angles is half the difference of the measure of the intercepted arcs. So when our vertex was at the center, it equaled the intercepted arc. When it was on the edge of the circle, it's half the intercepted arc. And when we pull the vertex out of the circle, it's half the difference of the intercepted. Notice now how it says arcs plural, because when we pull the vertex out, now we're creating two intercepted arcs. So there's three different ways that outside angles can be formed. The first is that they can be formed by two secants. That's what's happening in this picture. And our intercepted arcs in this picture are right here and right here. So the intercepted arcs are the ones that basically get formed by the edges of the angle, or by the sides of the angle. The picture in the middle here, this is a picture of an outside angle that's formed by two tangent lines. And these intercepted arcs would be this one and this one. So they actually end up making up the entire circle, because the tangents are hitting the circle only at one point. The intercepted arcs in that case actually create all 360 degrees of the circle. And then the last picture is formed by a secant and a tangent. And our intercepted arcs here would be this one and this one. Okay, so let's look at a couple of examples of using this property. All right, so to find the measure of angle 1 in problem number 1, so it's outside of the circle. So we're going to do the difference of the two intercepted arcs, and you always do the bigger one minus the smaller one. So 92 minus 43, and then we divide that in half. And so that gives us in this one 24.5 degrees. Okay, number 2, so same thing. The angle is outside of the circle. So we're going to do 72 degrees minus 22 degrees divided by 2. So that would be 50 over 2, which is 25 degrees. So in the last picture, this time instead of looking for the angle, we're actually looking for one of the arcs. So we're still going to use this same formula. We're just going to have to solve a little bit instead of just plugging right into it. So our intercepted arcs here are 200 and x. So 200 minus x divided by 2 would give us the outside angle, which is 72 degrees in this case. So we just need to solve that little equation for x. So 200 minus x equals 144. Just multiply the 2 to the other side. And then that would make x 56 degrees. So just like with inscribed angles, you can apply the formula in either direction. You can use the formula to find the measure of the angles, or you can use it to find the measurement of the arcs. All right, so if you look at the next page in your packet, this is the page that we are going to skip. So you don't need to worry about the examples on that page. The next part of your assignment in your agenda this week is going to relate to the 10.3 practice. And so I'll have a new video up on that will go through some of those examples and help you with that. Okay, so again, don't get overwhelmed. We're going to do plenty of practice, I promise. So that is it for these notes. So I'll see you guys later.